Welcome to Rges Algebra 2. This is lesson 1.6, Inequalities. Now we've been talking about solving an equality. An equality is a sentence, a mathematical sentence with an equal sign. Now when we go and we replace that equal sign with a greater than, less than, greater than or equal, less than or equal sign, we've now made the sentence, the mathematical sentence, an inequality. To solve inequalities, we usually demonstrate the solution with a graph on a number line. Why is that? Well, if I were to say that x is greater than 5, it would be very hard. I could say it in set notation, all x's such that x is greater than 5. That would be totally legitimate. But I could also do it on a number line where I say 0, I have the number or the value 5, and I want to indicate everything greater than 5. Notice that everything greater will be an infinite number of numbers, an infinite amount of numbers. So it would be 5, or well, not 5, it would be 6, 7, 8, but it also could be 5 and 1/10, 5 and 100th, 5 and 1,000th. You get the idea, on and on and on, an infinite variety. So we would graph that either with an open or a closed. We'd put our 0, we'd put our 5. If we want to indicate greater than 5, I would put an open circle, meaning do not include the number 5, but include everything greater. This would indicate x is greater than 5. If I wanted to say x is less than or equal to -3, I would graph my 0 on the number line. I'd graph a -3 on the number line. The 0 is really kind of my own convention. You don't have to graph the 0, but you do have to graph or indicate the number -3 on the number line, and then you would include the 3. So to indicate that I want to include the 3 rather than not include the 5, I would put what we call a closed circle. I would shade in the circle and graph, if it's less than or equal, everything to the left. So hopefully that's familiar to you, and this is just a review. Now, if we have a problem, then there's going to have several different varieties of problems, and you will always do fine if you remember two things. One, if you remember our rule about multiplying or dividing, because division is multiplication of an inverse, multiplying or dividing by a negative number. What does that do to an inequality sign? Do you remember? By negative. Well, let's think that through for a minute. If I have x is greater than 5. There's 5. This is x is greater than 5. What if I multiplied this by a -1 on both sides of the equation? I would get negative x is negative. Well, let me indicate this a different way first. I'm sorry. Let's start off with something else here. Say I begin with 5 is greater than 3. And that's a true statement. What if I multiply by a -1? I would get -5 is greater than -3, multiplying each side by -1. Is that a true statement? If we look at a -5 on a number line and a -3 on a number line, is -5 greater than -3? The answer is no, because to be greater than on the number line, you must be to the right of the other. Okay, so this is a false statement. In order to make it true, I need to reverse the inequality. So the rule is, when you multiply or divide by a negative number with an inequality, you must reverse the inequality. And that's the reason why. Now, remembering that, let's go ahead and solve a problem. If we see the problem as an example 1, page 27, and it says 3x minus 5 is less than 16. Okay. Well, I want to go ahead and solve it like an equality in the sense that I will add 5 to both sides. I would divide by 3. Am I dividing by a negative number? No. So I would go ahead and leave it a less than sign, and we get 21 over 3, or 7. Then to graph my solution, I would have a 7. I would not want to include the 7, so I have an open circle, and I graph everything to the left. And that's exactly what they're expecting you to do. Let's look at a couple more problems. To solve this problem, which is example number 2 on page 28, I would have to multiply both sides, or divide both sides by -2, or multiply both sides by -1/2. So we're going to divide by -2. I'm dividing by, a negative, so I would need to reverse. Don't forget the equal. If it's greater than equal there, it needs to be less than equal here, because the equal part of it doesn't go away. Okay, so dividing by -2, 18 divided by 2 is 9, and of course it's got to be negative. Your solution set have a -9 here. You want to include it, and everything to the left. Number 3 says 3 is less than or equal to 2x plus 5, which is less than 11. Now let's think about what this is saying. This is saying that some expression is going to be less than 11, less than a value, and greater than or equal to a value. So it's going to be here. I would not put 11 here and a 3 there, because I'm not taking into account the whole expression. If I just said x is less than 11 and greater than or equal to 3, I would graph it just like that. But because I have 2x plus 5, it's going to shift it, but the relationship of the two numbers will stay the same. Closed circle on the left, open circle on the right, and we're talking about all the values in the middle. The question is, what really are these two values? Not 11 and 3, but what? How do I solve that? Let's go ahead and look at that. I'm going to do it to both sides of the equation. In other words, when I subtract my 5, I'm going to do it over here, and I'm going to do it over here on both sides of my inequalities. So, subtracting 5, I'm going to get -2 less than or equal to 2x less than 11 minus 5 is 6. Now what do you think you'll do? You will divide by 2 to get it down to the x, but I've got to do it on both sides. Okay. So to divide by 2, I get -1 is less than or equal to x, which is less than, divide by 2, 3. So now I know that these two values on my graph are no longer 11 and 3, but 3 and -1. And hopefully that makes sense to you. You'll be practicing a couple of those, and if you need to see that again in class, we can. Now let me go to the next page and do a couple more problems. The next example says square root of x, absolute value of x is greater than 29. Now let's think a minute what that means. When we think of absolute value, we're associating it with the distance from 0 on a number line. So what are we saying? If that's 0, it's either greater than, there's 29 in that direction, it's either greater than the 29, I should be shading it right there, greater than 29, Or what's the same distance on the other side of 0? Negative 29. Do you think it would be greater than the negative 29? It's further away. It says the distance of the x is further away from 0 than the 29 than a distance of 29 in both directions. So on this side, I would shade it open, and on that side. So that's my solution, actually. Okay. Next problem would say, what if I have the absolute value of x is less than 29? By the same logic, let's just look at our 0. I'm saying that the distance of x from 0 has to be less than 29 notches. That means it would be less than on this side of the 0. And what would it be on this side? The distance from 0 would be to negative 29, and the distance of the x wants to be less than that, so it would be shaded this side. So that would be the solution set of that statement. And we have a couple more. Now, when we have an expression with an absolute value, and we're saying that that whole expression is less than or equal to 13, what does that mean? It means if I'm thinking about my number line, I have a distance of 13 here and a distance of 13 there. Right? So this would be 13 and this would be negative 13. And somehow my solution is going to be between them, a distance less than that. Okay, less than or equal to, so of course we'll have closed on this. But just like before, because we have an expression and it's not just the variable, it's not just x in there, we have a whole expression, we have to solve this. Now to solve this, it's not going to really be 13 and 13, or 13 and negative 13. We're going to reset up that, and we're going to be thinking about 3x. Notice I'm removing the absolute value sign. It's either going to be less than or equal to 13 or greater than or equal to what? What was on the other side? This was 13 and this was negative 13. So it's got to be greater than or equal to negative 13. So we solved this like we did the one where I said, okay, we're going to add 5, but don't forget we added in both directions. So we end up with 3x less than or equal to, adding 5, 18, greater than or equal to, negative 13, add 5 is negative 8. Now we divide by 3, and we're going to get 18 thirds, which is 6, and on this side we're going to get 8 thirds, negative 8 thirds. Okay, so my answer, if I'm asking for the answer in real numbers, I would have less than or equal to 6, greater than or equal to, what would that be? Negative 2 and 2/3. I could just leave it 8 thirds here. Greater than or equal to, right? And everything in between. Now, what if I told you that the domain, however, if the domain was real numbers, that's what I'd get. If the domain was positive numbers, which one's the positive number? Okay. Well, only the 6 is a positive number. So it would be less than or equal to 6, and this solution, the 8 thirds, negative 8 thirds, goes away. So I have to just bring it down to the 0. Put an open value at the 0, and I can only graph this section of it because that is my only valid answer. My very last question would be, what if I'm only looking for a domain of integers? Well, what are the integers? The integers would be all the integers included in that realm. Only the integers, okay? So if this is 0, okay, we're going to have 1, 2, I better go back and do that again. I'm going to need a longer line. 6, 5, 4, 3, 2, 1. 0 is an integer. Okay, what about on the negative side? Well, -1 is within this realm, within the range of -8/3. -2, what about -3? No, that will not count because that would have to be -9/3. So all of these would be my answers if my domain, and notice what I'm doing, I'm only graphing integers in that case. Positive numbers, notice I shaded it because positive numbers would include ratios, right, and irrational numbers. All right, so take a look at that very closely. Do your work carefully.